and and we should be live if I'm not wrong. Let's see. Alright, there we go. I'm gonna keep going till my laptop runs out of battery today. There we go. I'm gonna pick up right where we left off yesterday, actually. So, go ahead and open it. Oh, you got one viewer. Hello. What is this? Alright. CTC lost functions. Okay. This is context aware translation models. We don't really need that, right? Is this? Yep, there we go. Oh, we have one viewer again, I see. Hello. Type in chat. Alright. Let's see. Optimizations, adaptation to Mandarin. Look ahead and unidirectional. Alright, let's take a look at how they're working out their back propagation and normalization. I think this is sorted out as back propagation, not sure exactly. Wait. Experiment training. Very. Yeah, it is technically back propagation, would be reducing the cost. Sweet. Alright, let's take a look at it. There's also, we saw model architectures yesterday, and it's recurrent networks, convolutional. Yep. So we're gonna. The inputs to the network are a sequence of log spectrograms of power normalized audio clips. What are power normalized audio clips? Let's take a look at that. Convolutional networks operator seem to have. Wait. Streamline. What is a power normalize? Is it just a normalize? Normalize? It seems legit. Let's see how that is done then. Ooh, okay, there's quite a few. Begin is changed to. Oh, okay. Thought someone was there. Let me just really quickly. Being the average amplitude to the target level, this average is a simple measurement of average power. Okay, yeah, it's basically this. This is RMS value. It can be a measure of human perceived loudness, such as that offered by replay gain. A proposed standard published by sound check. Alright. Um, seems legit. Alright. So YouTube's reference level is loudness k-weighted relative. Oh, okay. So if a program is analyzed to be, YouTube will lower the level by 4 decibels to bring it to the reference. Okay. Loudness normalization was created to combat varying loudness while listening to multiple songs in a sequence. Before loudness normalization, one song in a playlist must be quieter than the rest, so the end listener would have to turn up a volume knob to adjust the playback volume. Okay, so in order to make sure everything's pretty much the same, same audio level, we're just lowering the volume there. That seems true. I wonder what volume would work for it. The outputs are the letter alphabet of each language. So, as an output, it can be like no. Actually, let's keep it character so we can get a string builder output. Outputs is equal to it's gonna be annoying. Get it? Please be I'll stop. Sorry. E F G H I J. I don't know if this is how I'm gonna get the output as, but I'm gonna keep it like this. K L N N it would be really embarrassing if I forgot this right now. E Q R S T U V W X Y Z. Right, I'm just gonna start dropping the there we go. Oh, I put double commas there. I'm a very nice person. There you go. Excuse me. Alright. Someone's viewing the stream. Who is this? Would you like to chat? Would you like to put something in chat maybe? 7 a.m. We're also doing a CTC loss function, which we already covered, yes. Alright. At each output time step t, the RNN makes a prediction where LT is either a character in the alphabet or the blank symbol. We also have ABC to Z, space, apostrophe, or blank. So we'll also have blank there. Apostrophe is something I don't know how to implement yet, but didn't. For example, let's take didn't for example. It consists of did not, but I guess I'll leave it in there. But I don't know how you would actually recognize an apostrophe. Well, let's just leave it in there. Didn't. Maybe if it comes across a word like without the apostrophe, it would predict something like a didn't, which then it would convert to a didn't like that, maybe. Seems legit. Alright, okay, try that. Oh, I said update. I never liked those. Maybe add the space symbol to denote word boundaries for the Mandarin system. Yeah, Mandarin. I guess Chinese is a little really. Chinese is weird. Chinese, correct. Just look for some. Yeah. Breaks your head when you look at it. Let's go to images. Take a look at their newspaper. Yeah. How do you even work with that? Jesus Christ. Alright. Chinese characters. Most of our experience use the bidirectional recurrent layers with clipped rectified linear units with a max okay, with ReLU basically of 20. Why would it alright, maybe it's because of the 20 ms Windows. Not sure why they would use 20 here. We let's predict directly the sequences of characters from the input audio. Alright. Inference CDC models are paired with a language model trained on a bigger corpus of data. We are using a specialized beam search algorithm to find the transcription Y that maximizes. And then we have this, where WC is the number of words or characters in the transcription Y. The weight alpha controls the relative contributions of the language model and the CTC network. Okay, the weight B encourages more words in the transcription. These parameters are tuned on a held out development set. Alright, okay. So we also have a CTC, or no, we have a beam search algorithm. What is a beam search? Ooh, okay. A beam search decoder. How to implement a beam? Oh, okay. It's something that already exists in. So we don't have to reinvent the wheel here. It saves a lot of trouble. Let's head over there and see what up. I just should go directly to the PDF. There's quite a bit in here. Let's take a general look at what it is. Iteratively generates new hypotheses, corrections from the current hypotheses, and scores them based on the features of grammatical correctness and fluency. These features include scores from discriminative. Whoops! YouTube, please don't flag me. Discriminative classifiers for specific error categories such as articles, prepositions. Unlike all previous approaches, our method is able to perform correction of whole. Hold on, let me just get a good song going. Can we not? Can we really not get a good song going? Alright, and like all our previous approaches, our method. Oh, I'm so getting flagged, aren't I? And like all previous approaches, our method is able to perform correction of whole sentences with multiple and interacting errors while still taking advantage of powerful existing classifier approaches. Our decoder achieves an F1 correction score significantly higher than all the previous published scores on helping our own shared task data. Now, honestly, I want to see how it does that, so let's go over that a bit as well. Shall we? Give me a few seconds. Let me get a good sound going. There we go. There we go. This is an important problem in natural language processing that has attracted yeah, okay, right. Ooh. Each classifier corrects a single word for a specific error category individually. This ignores dependencies between the words in a sentence. Also, by conditioning on the surrounding context, the classifier implicitly assumes that the surrounding context is free of grammatical errors, which is often not the case, right? Because, okay, let's face it, we've all said broken stuff before. And, yeah. Finally, the classifier typically okay, I keep losing my track of thought. Never mind. Basically, one best prediction is not able to change its decisions later or explore multiple corrections. Instead of correcting each one individually, we would like to perform a global inference of corrections of the whole sentences which can contain multiple interacting. Okay, you know what? For the sake of simplicity, I'm actually gonna draw and explain what that actually meant. So, assume we had quite a few words here. So what the CDC beam search basically does is, first of all, well, referring from this paragraph, what it does, the first line is basically saying that all the stuff before used to ignore these words to guess the next word, right? But the observed word is replaced by the prediction. Although considerable progress has made, the classification approach suffers from some serious shortcomings. Each classifier corrects a single word for a specific error category individually, so it's not considering the words before it for context, right? It's doing it individually. This ignores dependencies between the words in a sentence, what I just said. Also, by conditioning on the surrounding context, the classifier implicitly assumes that the surrounding context is free of grammatical errors. What's happening here is that it says that the classifier is assuming that this sentence up till here actually makes sense and is not grammatically incorrect. Like, for example, it's assuming that if I say a sentence going, the what the hell? Okay, I guess I can't type anymore. Alright, never mind, I guess. Basically, if I say a really weird sentence such as the jump fox over, right? That really doesn't really work, does it? Because it's grammatically incorrect. Which is often not the case. Yes, it's often not the case. As a human, we already know this phrase. So, over the fence, or you can say the brown. Oh no, it was what was it? The sleeping dog. So that's what the CDC beam does. It takes into account the previous context, which is pretty nice actually. What I would like to add to this, to be honest, would be what humans do as well. Since the CDC beam search algorithm relies on previous words, what I wanted to do was add a simple context to the entire paragraph that we are saying. So, you know how us as humans, for example, if someone's talking about a color and you miss out on a single word, you take the sentence that they are saying, right? Suppose this is the word that you missed out. You know they're talking about the colors, right? You also know a bit of the sentence that they said. You can easily guess that this word that they said fits into the sentence and is related to the word color, which makes it much easier to well, to be able to guess what the word is with more precision, you see. And that's what I actually want to try implementing here, because again, more accuracy. And I feel like having a context as to what someone is talking about is gives it a gives the machine learning thing a it gives the AI a better idea of what object is being talked about here and how it could possibly react to it, you know. So we'll have to find out a way to figure like add that in, you know. Shouldn't be too hard, but I'm assuming it'll be pretty hard though. So right. Alright. An alternative what is that word? Okay, hold on. From ow. Alright. An alternative what is this? Ah. Is to view error correction as a statistical machine translation problem from good back to good English. While this approach can naturally correct whole sentences, a standard SMT system cannot easily incorporate models for specific grammatical errors. It also suffers from the paucity. Um. Okay. Of error annotated training data for grammar correction. As a result, applying a standard SMT system to error correction does not produce good results, as we will show in the work. In this work, we present a novel beam search decoder for grammatical error correction that combines the advantages of classification approach and SMT approach. Oh crap, I completely forgot to record. Gee. Alright, anyways. The classification approach and the SMT approach, starting from the original input stream, the decoder performs an iterative search over possible sentence level hypotheses. Actually, I probably do not need to record since the stream will be there anyways. In each iteration, a set of proposals generates a new hypothesis by making incremental changes to the hypotheses found so far. A set of experts go, alright, so it goes on about stuff, SMTs and stuff. Okay, so what this basically does is that it has two components. A The CDC beam search algorithm has two components. One is the proposer, and the other is the experts. What happens is that, and then we have the input data from before. Input data from before is fed into the neural network, which then generates a bunch of hypotheses which generates a bunch of hypotheses that could happen, and then the experts are fed this, and these actually mark these hypotheses as which could be more likely. So this could be 0.8, 0.5, or not really 0.5, but 0.1 maybe, 0.05, 0.05, where the total sum is always equal to 1, I believe, because yes. And then this gives you an output of what could appear next, which is again then probably fed straight back into the inputs. Right. Each hypothesis corresponds to a complete sentence. So they're literally completing the sentence. Excuse me. Completing the sentence. That was painful and slow. Like POS tagging, chunking, and dependency parsing, which provides necessary features for the expert models. Right. Now, we've lost the viewer who was here actually. Oh well. I wonder who that was. Is there a way to check actually? Not sure. Participants. Oh well. Wait. Alright. Alright, let's go back. Alright, so the highest scoring hypotheses are kept in the beam search for the next iteration. Yep, that's what I said, but it feeds it straight back up. The search ends when the beam is empty or the maximum number of iterations has been reached. The highest scoring hypothesis found during a search is returned as the sentence level correction. We'll read up a bit on proposers and experts, and we'll go back to working. Actually, we quite need. Oh, Jesus Christ! We might actually need this. Hold on, I'm gonna read. We might have to read the entire paper here. Biscuits were the best thing. Now I need water, I'm an idiot. Hold on, let me go get some water. There we go. Amazing. Alright, so instead each proposers makes a small incremental change to the hypothesis in each iteration. Alright, change corresponds to the correction of a single word or phrase. So the proposers basically either add a word, plus word, minus plus, so basically change the word. Oh, hey, someone's back. Hello. Or plus a entire phrase. Oh, I guess you can't spell phrase. Or minus plus another phrase. Alright. Additional proposals for other error categories can easily be added to the decoder. For spelling, replacing a alright. For articles, alright. For prepositions, for each prepositional phrase, PP, generate a new set of hypotheses by changing the observed preposition. Okay, we'll get back onto this later. Punctuation insertion, insert commas, periods, and hyphens based on a set of simple roots. Sir, whoever's watching the stream, do you wish to type in chat? Just put a hello or something. Quite curious as to who you are. Insert commas, periods, and hyphens based on a set of simple rules. Anyways, thanks for being here today. Noun number for each noun, change its number from singular to plural or vice versa. Alright, experts. Experts score hypotheses on particular aspects of grammaticality to help the decoder to discriminate grammatical hypotheses from ungrammatical ones. So basically, what it's doing is that it's taking whatever's the proposer said, right? So I bet probably words and phrases there. What it's doing is that it's like taking the entire sentence and seeing if it's actually grammatically correct. If it's grammatically correct, it probably just boosts its probability of being the right thing, and if it's not, it reduces the probability of whatever is being spoken there. We employ two types of expert models. The first type of expert model is a standard Ngram language model. Okay. And so basically what the Ngram language model does is basically, okay, you guys have seen how autocorrect works, right? That's basically an Ngram model, where it checks the last three words you've seen and predicts the next word based on the last three words. That's basically an Ngram model, where n refers to how many words it's going to check backwards. The language model expert is not specialized for any particular type of error, so it's not checking if it's a grammatical error or syntactic. Okay, do syntactic errors exist? I'm not sure. Maybe. The second type of experts is based on linear classifiers and is specialized for. Okay. So first we do like a overall check, and then we do like a particular check. That's not bad. It's not bad. We use the following classifier experts in our work. Alright. The features for classifier expert models include features from Ngrams, part of speech tagging, chunks, web scale, Ngram counts, and dependency parse trees. I'm wondering if we could. Alright, never mind. Article expert, predict the correct article for a noun phrase. Alright, so basically your us and ands and those. Preposition expert, predict the correct preposition, and you have your noun number. Predict where a noun should be in singular or plural form. Again, that I guess refers to article expert, where it could be a mango or, well, a few mangoes, I guess. Or rather, a house or houses, I guess. A home or homes, where this actually determines where the noun, you know what I mean, right? Each hypothesis is associated with a vector of real valued features, which are indicators of grammaticality and are computed from the output of the expert models. Wait, you guys can still hear me, right? Yes. Wait, you guys can still hear me, right? Right, good. We call these features hypothesis features to distinguish from the features of the expert classifiers. The simplest hypothesis feature is the log probability of the hypothesis under the n-gram language model expert. To avoid a bias towards shorter hypothesis. Wait, I lost. Shorter hypothesis, we normalize the probability by the length of the hypothesis. Where h is the hypothesis sentence and h is the hypothesis length in tokens. 1 by length of the tokens log with the probability of it being h. I wonder how it actually helps, but I'll take it. Okay. For classifier-based experts, we define two types of features. First is the average score of the hypothesis under the expert model, where U is the expert classifier weight vector. Okay, wait. Chill out for 2 seconds. Holy crap. For classifier-based experts, we define two types of features. The first is the average score of the hypothesis under the expert model. Okay, so we take the average score of whatever is actually the thing. Like how well the sentence fares. Second is where U is the expert classifier weight vector. Okay, so I guess that's a vector that is trained. I believe, I hope. U. XHI and YHI are where I believe H is still the hypothesis sentence. I would actually like to note this down. I'm just gonna write CTC beams search algo. I'm just gonna go ahead and copy this because I have no clue how I would write it. Jesus Christ, it's broken. We're gonna have to. Let's write it ourselves. 1 by n with some while iterating through. I guess I could just do it like that. Never mind, I guess. Screenshot. Paste. You know what? I'll actually change it up in Paint so that I can actually just tell what is what instantly. Proportions, am I right? Where n is basically, Jesus Christ, chill out, smaller. Excuse me, my bad. where you, okay, what is n exactly? Alright. Okay, wait, hold up. Yeah. 1 by n. N. Wait, okay, so we can probably. Let's try doing it the other way where I try to figure out what n is first. I did not mean to do that. Okay, so here, u is basically weight vector for the expert classifier. Your x with the subscript, right, is a subscript with I and a superscript h. Right. H would be, what is the shortcut for this? It is no clue. This would be feature vectors. Feature vectors. Observed class respectively. Okay, so this is the feature vector while y of h and I is the observed class. Now, what exactly is an observed class? Observed class. Put that down there. For the ith instance extracted from the hypothesis H, where basically n is the length of the sentence H, where I is each word during iteration. That's what I hope it is. That's what I'm assuming it is. Where and F is basically a feature map. Basically, looks like convolutional. What? Convolution network. An idiot. Convolutional network. Right. Right. That was dumb. Feature map, right. The average score reflects how much the expert that computes expert classifier features takes care of the classifier features, which are basically your POS tagging, chunking, etc. Dependency parsing, etc. Right? The average score reflects how much the second expert score, we call the delta score, is the maximum difference between the highest scoring class and the observed class in any instance from the hypothesis. Generally speaking, the delta score measures how much the model disagrees with the hypothesis. Okay, so what they're basically doing is that there's one part which decides how much it likes the sentence and gives it a score, while the second part basically criticizes it. Can't spell apparently. It's in S. Where did I miss? Oh, it's C. Okay. Criticizes it and basically output how much it hates the score slash how wrong it thinks the score is. What song is this? I like it. For example, there is a feature that counts how often the article correction E the has been applied. Oh, okay. Finally, each hypothesis has a number of correction count features that keep track of how many corrections have been made to the hypothesis so far. For example, there is a feature that counts how often the article correction the has been applied. We also add aggregated correction count features for each. Sorry, the song got to me. We add aggregated correction count features for each error category. For example, how many article corrections. So how many article corrections, how many grammatical corrections, how many syntactic corrections, etc. etc. The correction count features allow the decoder to learn a bias against overcorrecting sentences and to learn which types of corrections are more likely and which are less likely. Alright. Mr. Stream Viewer, you've been here quite a long time. For a good 18 minutes. Thank you for being here for this long. I appreciate it. And this is probably it's probably in the background, but I still appreciate you being here. It's 7:31. I'll probably end the stream at 7:45 or something, or whenever someone wakes up. Alright. The correction count features allows the decoder to learn. Alright, we did that. Then we come across to the decoder model, which I do not believe we need to do. Actually, wait, what? Okay, hold on. This actually explains a bit of how it's working. They might be right. Score of 10, E of an, the, at, for, with, and okay, so they're basically fixing it in an other. So obviously it can't be in an other. So the score instantly goes to a -1. In the other hands, that again is probable, but this actually is very correct as well. At other hands, for other hands, with other hands, and in other hand. Normally it would be in the other hand, but in the other hands they might be right, which does sound better than in other hands they might be right. So it would take this and then feed it back into the network. At the other hand, for the other hands, with the other hands, in the other hand. Well, in the other hand, they might be right. Which then goes in another hand, at the other hand, for the other hand, into blah blah blah, on the other hand. So this is how it fixes it. As you might clearly see, in becomes on, so on the other hand, they might be right. Which is quite interesting how it took in other hands and converted it to on the other hand. That's quite interesting, to be honest. That's very amazing. Some hypotheses are omitted. You just probably got extras here. About the other hand, by the other hand, to the other hand. Normally, I didn't think it would go further than this because this really is the most correct one out there. You could also, I'm not sure if this is actually true, so I'm just guessing here. But you could very clearly see that each score is higher than the previous one, the one which it actually chose. But then over here, it didn't go further because the score is actually lower. All of these, since 2.4 it is less than this is less than, and so it ended right here, and hence the highest scoring hypothesis found would be this one. Quite interesting, in fact. Right. And the temperature of the system, or how hot it is, right? Right. That takes care of the beam. Sequence to sequence model, beam search. We could watch a video on it, but I would not like to do that right now. Is beam search greedy? Good question, actually. It's the best reduces. It is thus a greedy algorithm. For those who don't know what a greedy algorithm is, I would just. So basically, what it does is that. Yeah, basically, it doesn't like. I don't know how to explain it actually. Hold on. It's probably some page that explains it really nicely. Yeah, basically, what it does is that it, for example, you know how a good example would be if you are, for example, a good option, right? I guess it's more like a story RPG thing. If you've ever played a dating simulator or anything, where you would actually just you're presented two or more options, right? And you would pick the best path for the story to go forward. That's basically a greedy algorithm where it instantly picks the right option uh, instead of how game, what do you call them, game states work, where it picks each option and checks which one, or technically it does do that, where it picks each option to see which one's the best. That's pretty much it. There's nothing much to it. It just tries to make the best choice at each. Again, we saw it in the paper itself. If you can go back to where that was, I'm never gonna find it. Yeah, you can see where it's instantly making the best choice and going forward with it. It's not bothering with the others too much. How to implement art? Let's take a look at this as well. What is the random picture? Natural language processing, yep, we get that. Yes, sir. Now, what is this? First of all, we start with the prediction problem that involves a sequence of 10 words. Each word is predicted as the probability distribution over a vocabulary of 5 words. Okay. Okay, over here I believe we would. Alright. Therefore, the task of decoding becomes the task of selecting sequence of integers and the word distributions. Oh, okay. So basically, a sequence of 10 words over a vocabulary of 5 words. So basically, this is the output from our neural network right here, with each of these referring to a single word in the entire thing. So for example, we could have 5 words. For example, these 5 words, and they're encoded as numbers. So 0.1 is probability, 0.2 is distribution, 0.3 is over, etc., etc. Well, assuming the words have been integer encoded, so basically that's what they're referring to. So that the column index can be used to look up the associated word in the vocabulary. So basically, I believe what's going on here is the column index also. I'm not sure what that line exactly means. We'll get to know it soon enough, I guess. This one concurrent viewer is really piquing my interest. So you've been here for quite a bit. Oh crap, I closed the stream page. Crap. Okay, we'll connect it back. Okay. Jesus. You've been watching for quite a bit. You've been watching for quite a bit. Okay. 10:37. What? Excuse me. Not you. Who is this? Excuse me. Not you. Who is this? Excuse me. And you can probably hear the background me replaying my stream. Right, I should not be doing that. Alright, so the greedy decoder function below implements this decoder strategy using the argument max function. So return argument max for s in data. Alright. Is listed below. Seems legit. 40404040. Another published upon research. If greedy is the most likely step, and keeps key most likely by case is okay, seems legit. Right. Such progressing Hall for each candidate separately are by reaching a max balance, by reaching an end of token sequence, or by replacing a threshold likelihood. Let's let's make this concrete with an example. We can define a function to perform the beam search for a given sequence of probabilities with the beam width parameter k. At each step, each candidate sequence is expanded with all possible next steps. Each candidate step is scored by multiplying the probabilities together with the k sequences with the most likely probabilities are selected and all other candidates are pruned. Basically what I explained here, this stuff again. It's the exact same. Very nice. Now, repeats until the end of sequence, probabilities small numbers, and multiplying small numbers together, creating to avoid underflowing floating point numbers. The natural logarithm of the probabilities are added together, which keeps the numbers larger and manageable. Further, it is also common to perform the search by minimizing the score. The final tweak means that we can sort all candidate sequences in ascending order by their score and select the first k as the most likely candidate sequences. The beam search decoder function below implements the beam search decoder. Here we go. Let's see what it does. So beam search decoder data comma k sequences will be a list. Okay, and 0 0. What's on? For a row in data, so for each row in the data that was implemented, data being this again. Go back. All candidates equals list. What does list do? Alright. I'm never gonna find where I was going to pull it out. Alright. Expand each current candidate. Alright. For I in range length of sequences. Okay. For j in range length of rows, candidate is equal to seq plus j score minus. Okay, that's kind of going over my head a bit. Hold on. Okay. It's not too hard. Basically, it's taking sequences or whatever the data is, and the lines basically, and walk over each step in the sequence. So basically, it's going through all the sentences, and basically, sequence is basically your sentence, and the score sequences of I. So you can see your main whatever sentence it is, and how much of a score it has. Is basically what's going on here. The candidate sequence plus j and score minus log of row of j. All candidates are scored. So that it sorts all the candidates it gets and returns this. And then I believe it just sends in data. What's this 3 from? They explained k somewhere, wait. Yeah, beam width parameter, right? I think it's just checking 3 at a time, not sure, but it does something. Select k best, ordered k. Right. So basically what's going on with this. Right, anyways. All candidates sorted by score. Select the k best. Define a sequence of 10. Yep. Data is equal to array of data. Decode sequence result. Print the result. So then it will print out whichever one's the highest probability by the lowest probability. I believe. Actually not. It gives you the probability of which one could be the highest. These two are the same. Okay, that's not a very hard thing to do actually. We could. Alright. Intuitive explanation. Oh, come on. Alright, we're getting somewhere. Okay, so things we covered today would be. I'll fill in stream 1 after. Um. It's buffering. That's not good. Can we get my stream quality back? Is the stream back? Alright, it's back, nice. Okay. I'm kind of scared me for a bit. Thought my internet died. I'll fill in stream 1 after the stream ends because I don't really remember. But for stream 2, we actually covered up quite a few things. First, we covered the beam search algorithm, the decoder. We covered how it works and how it's implemented in Python, plus how we can implement it ourselves. Then we also learned about I hate how it does that. There we go. Then we also learned about what else did we do? Not much. We decided the outputs of the network. We basically did a bunch of beam search algorithm stuff today. I'll fill in whatever I haven't written in a bit. Because we didn't do anything much regarding the main program itself, did we now? It was mostly about all of this stuff. Where we took a look at the beam search algorithm, which is actually, quite frankly, a very important part. So for tomorrow, I think we can since we're done with the beam search, tomorrow I guess we can focus on the fast Fourier transforms and the audio part of the stuff, where we record 20 milliseconds of voice every I believe 20 milliseconds, and then we convert it into each utterance. Was it 20 milliseconds? Yeah, 20 milliseconds window. So then we can convert it. And then by day 4, we should be recording. By day 4, I'll keep a few things recorded so that we can train the algorithm. We should be done in a week, I believe. Nice. It's actually very nice, actually. Alright, so I'm gonna end the stream here. Thanks for whoever was here. I really appreciate you being here, and I'll see you later then.